introductions. So today our sponsors are Capture Technology, Improving Texas A&M Cybersecurity Center, Innovation Underground. We've got HTRI, ISSA, T-Star, Electronic Systems, Engineering Technology, and then obviously the Grand Stafford Theater, which is where we're at. And then our speaker today is Vansh. We want to give him a round of applause. He will give an excellent presentation.
Howdy, how's everybody doing tonight?
Good.
Awesome. Okay, so I'm super excited to be here to have the opportunity to present some of the work that I've been doing over the past couple of months. Thank you, Mr. Quintana, for hosting me tonight. I'm again, really excited to be here. So the title of the presentation is Unlocking Enhanced Perception for Autonomous Vehicles Using Generative Adversarial Networks. That's kind of a mouthful. I'll be sure to kind of specify exactly what it is and some of the things that I did to approach my project. But basically, one of the things about me is I'm a huge car guy. That's been part of my life forever, since I was 4 actually. And so I knew that in my future I wanted to work on cars. And one of the things that really struck my interest in the past couple of years was the advent of autonomy and ADAS, as we're seeing it in our day-to-day lives. Does anybody here own a Tesla by any chance? Oh, okay. All right. Well, the systems like autopilot, things like Ford's Blue Cruise, they're starting to hit the markets and they're generating a lot of buzz. We also see a little bit of controversy with autonomous vehicles, with some recent incidents with Cruise. And so I think there's just a lot to be said about where autonomy can take us in the future and its benefits. And so I wanted to work on something that might help that or maybe accelerate that sometime in the future. And that's where kind of what my motivation was. And so I narrowed it down a little bit more into perception, or computer vision, right? How robots are able to see and perceive the world around them. Right now, right, like Ford's Blue Cruise or Tesla's autopilot relies primarily on stereo vision or RGB cameras for perception. And so one of the things that I found through a good amount of literature review is that these sensors struggle a little bit in shadows and fog, as well as other adverse lighting environments. Which is kind of unfortunate. There's a lot of really advanced algorithms out there for RGB, but it definitely could be better. And we also have the ability to use sensors that have far greater capabilities right off the bat, and then enhance them even further to get a fully comprehensive view of what's around the eco vehicle. So sensors are kind of classified into 2 different categories: passive and active. RGB cameras are passive because they absorb electromagnetic waves. They basically take in what's around them in the environment. But there are also active sensors. So LiDAR and radar are good examples where you're emitting something and then waiting for kind of a signal to come back in order to determine time of flight, just to be able to create like a point cloud around the vehicle. They also have their own limitations. They are very expensive. There are a lot of companies that are kind of targeted towards making them cheaper and more accessible. But for LiDAR and radar, there's things like phantom clouds. And so, if there is fog, you might have like a laser beam reflecting off of like a water particle. That could also sometimes deteriorate the quality of what the vehicle is able to see around it. So the problem at hand is, do we have a better cost-effective perception solution for AVs that is passive? So how can we receive the most amount of environmental detail from what's around us? And one thing that's currently out there for that is hyperspectral imaging. That's currently being explored as a potential replacement for current sensors. And so I'll talk a little bit about what exactly hyperspectral imaging is. But again, the motivation is how can we enhance the performance of that imaging type to be even better than it already is. And so I did a little bit more of a deep dig into what potentially could be improved for it. And so one of the things that I was guided towards through my PhD student and some of his contacts was shadow removal, as well as illumination and variance compensation. So basically just like getting rid of shadows or just like having like seeing contrast corrected for it. Again, right now, since hyperspectral imaging is very new, there's just a lack of algorithms that is dedicated towards the technology. So what is hyperspectral imaging? I talked a little bit about RGB imaging. So you can see on the right, there's a red, green, blue picture, which is what all of your iPhones or Androids can take. It gives you 3 intensity values, red, green, and blue. And that's about it, right? For hyperspectral imaging, it can give you a lot more. So it captures this continuous spectral curve. You have not just 3 bands, red, green, and blue, you have all the way up until 160. In my case, I'm using an imaging system that has 51 bands, but 3 bands is only 6% of that, right? So I'm able to capture a lot more, which gives it implicit protection against environmental disruptions. And this means that each entity within the image, each pixel, has this distinct spectral curve. So for each pixel, I have a curve, right? And it captures information not only from the visible light spectrum, but from ultraviolet and near infrared. So if there's like an issue with being able to see at night, hyperspectral imaging has you covered, again, because of near infrared. So it is a really interesting technology. Right now, again, current imaging systems are not near where they are to be able to replace robotics perception systems. But the hope is, as it becomes better and as the technology develops, it could be a potential replacement. So I mentioned shadows a little bit earlier. I want to talk a little bit about how that is an issue specifically. And so this is actually a picture from a custom data set I created. And so this is like a first-person view, a very simple image of just a little toy bus within a white background. But you can kind of see, hopefully it's visible, oh, it is a bit dark, but there is a backup image on the left that shows you like for a given pixel that is in the shadowed region, we have like this downward curve that doesn't fully represent what it is without. And so we want to be able to compensate for each of these pixels and bring them up to its full fidelity. And so with that, if I have objects that are within the shadow, or I have materials that are within the shadow, segmentation algorithms or anything that does object detection might not be able to pick it up because of that illumination issue. And so we want to be able to try to correct for that artificially, which is where the whole generative adversarial network concept comes in. So kind of what the solution I came up with is, and what I'm still currently developing, is 2-tiered. So first, the first half of the work is developing a scalable GAN architecture to tackle a coarse removal of the shadow and illumination appearances. And so by coarse removal, I mean it gets about like 60 to 70% of the job done. It's very hard to be able to train again with hyperspectral images because there's no public data sets out there. Everything that I trained it on, I collected myself. And so this gives you a very limited view of what the GAN can do, but I can basically create the process so that I can refine it even further using a physics-based approach. That's what I'm currently working on right now. So you can do certain things like encode it and do dimensionality reduction for feature transfer. So if I have a coarse removal, I generate this shadow mask, and then I'm able to match pixels from the non-shadowed region to the shadowed region in order to get a full comprehensive reconstruction. And I'll have some pictures to kind of show what that process looks like. But for right now, the aim is to develop a continuous video feed with low latency. And so I'm able to take hyperspectral video in real time and then be able to process it in real time. And it kind of takes the form of like this UI that does all of this. But what is a GAN? So a GAN stands for Generative Adversarial Network. I can explain each term in it. Generative means that it's producing data. It's not like a classification network. It is creating synthetic data. And then adversarial is the way in which it is trained. And so it takes the form of 2 convolutional neural networks. One of them is called a generator, the other one's called a discriminator. And they're trained in game ideology, right? So on the left, there's a high-level overview. I think this was from Google. Of how a GAN operates, right? So you have real images that you take from a data set, and then you sample them, convert them into tensors, and then that is your source of truth. That is a ground truth. The other side of it is a random input that you enter into a generator, and that creates a sample. And so the discriminator's task is to figure out which one is real and which one's fake. Depending on what the result is, either the generator gets penalized or the discriminator gets penalized. So I would consider it kind of like an analogy to like an artist and somebody who's judging the art, right? So the artist is the generator who's producing, these fake images, and then the art inspector is the discriminator trying to figure out which one's real, which one's fake. And then the generator gets a point if it does its task correctly. The discriminator gets a point if it does its task correctly. And through that, you can do some gradient backpropagation and make each of those networks better and better at what they do, so that they equalize their losses. And at a certain point, nobody's really winning. It's like half and half. Like, hey, sometimes the generator is working better than the discriminator, and then vice versa some of the times. But yeah, there have been quite a few different cases through which it began. It's been really good for generating high-quality synthetic data. The detailed overview of what those networks look like is on the right side. So hopefully that's a good amount visible. But basically, you're taking an image and then downsampling it into a latent space, and then applying residual blocks in that latent space, and then re-upsampling it into what your artificial image looks like, right? And then your discriminator takes that artificial image, takes the truth, and then downsamples it down to a binary decision, which is real or fake. And depending on which one is which, again, all those losses are computed, and everything gets backpropagated so that both of them become better at their job. You can rearrange the way that, again, is traditionally made to do image-to-image translation. And so this was a really interesting paper that came out a few years ago called CycleGAN. And so this way, I don't have to tell it what's real and what's fake. I give it two domains, right? And so on the left, you have zebras and horses. I give it 1,000 images of zebras. I give it 1,000 images of horses. And the way the network is set up is that it basically, it's able to translate zebras to horses by the time it's done training. Right? You just give it an example of both, and it'll figure it out by itself. The same is true on the right, just a different example. It's Yosemite in the summer and then Yosemite in the winter. At a certain point, it's really good at being able to translate Yosemite in the summer to winter, and then vice versa, which is why it's called CycleGAN. And so I can adapt this for my purpose to be able to create two domains. One is I have an image that is in the shadow domain, and then an image that is in the non-shadow domain. And I give examples of both. And I tell the network, complete the task alpha to beta, which is basically, there's a mapping function that will translate a non-shadow pixel to a shadow pixel. What makes CycleGAN so powerful is the introduction of two more losses, which is identity loss and cyclic consistency loss. And so what I'm telling it to do is, instead of going from domain A to domain B and figuring out which one's right and which one's wrong, I tell it to translate it back to domain A. And then I measure what the difference is between the original image and what the final translated image is. And that's our cyclic consistency loss. Right. And I do the exact same thing in the opposite direction. And so to the right is kind of a little diagram that I created, and it kind of demonstrates all of that working together. So GR means the generator that removes the shadow. And so we have an image with a shadow in it, it removes it, and then it uses a binary mask that I'm using to guide the process to go back to the shadowed image. And then it does a shadow cyclic consistency loss, so it measures the difference between the first and the third, and that's used to backpropagate one of the networks to make it better. The other thing is an identity loss, and so if I tell it to basically translate an image from the domain to its original domain, or the exact same domain, it shouldn't change. So if I give it an image that has a shadow in it, and I tell it to shadow it, it shouldn't do anything else different to it. And so if it decides to do that, it's penalized as a loss. And then the adversarial loss is, again, the discriminator, which we just talked about. The exact same process happens in reverse, where we take an image, put a shadow in it, remove it, and then we have our three losses. And so the network that I have has a couple of customizable convolutional layers. I think it uses like a dense UNet structure, similar to how it was implemented with the original CycleGAN. But the big part of it is that it's adapted to hyperspectral imaging. And so here's some more of the semantics on how that works. So the first thing is, we have a couple of hyperparameters, and so when we launch our script to do our training sequence, we interpret and apply those hyperparameters, right? Things like learning rate, epoch decay, how many epochs we're training for. And when I say epochs, that's one complete iteration through the data set. And so if I have 64 images, one epoch is going through all 64. So traditionally, I've trained some of my networks for about anywhere from 2 to 500. It really depends on the size and how much variability is in the data set. Two, since I'm taking these images myself, I had to develop all the tools to reprocess and calibrate raw data, which was a lot of work. So the camera manufacturer is Qbert. I took all my samples with them. They have their own custom file format and their own SDK. So I leveraged some of their functions using a Python wrapper to basically do data set automation. So be able to take one of their custom images in their custom file format, and then be able to process what a reference to light is, what a reference to dark is, and then create PyTorch-specific tensors. And again, you would also have to resize some of the images, so doing like bicubic interpolation and then resampling would also be a part of that. Additionally, in order to make them PyTorch-specific tensors, you'd have to standardize the data set to reduce the effect of outliers, and so you'd also have to accomplish that with all 51 channels. The next step is to create batches to forward to the network, and so I can do batches of one image at a time, but I can do them by pixels as well. Actually, I would stick to just one image at a time. And so this is like loading and transformation of the data and then shuffling and matching domain pairs. So if I have images in domain A and domain B, I have a good amount of combinations of both that I can put together. And then I also have like random horizontal flip, things like resizing, just to be able to like give it some more variability in the data set. The fourth part is initializing the subnets. So if I'm reloading it from an epoch checkpoint, I can basically save my progress. And so if I start again from like epoch 460, I would load in all of my path variables and then continue training. Or if I'm starting from a fresh, it would basically just like respin up all these modules, set them up with like default weights, and then continue updating those weights as the training sequence goes. And then lastly, saving everything, making sure that we're not losing any valuable data is important. So saving the model throughout like checkpoints is another big thing that's part of the code. So yeah, what this actually allowed me to do was run all of this on a supercomputer at Texas A&M called Grace. So the department is called the High Performance Research Computing Center. And I use the Grace cluster, which lets me have access to NVIDIA A100 GPUs. This gives me a speed up of about like 7 to 8 times over what I can run on my laptop, which is really nice. So after I did some data collection, I have that little visualization off to the right. And so it's able to take an image with a shadow in it, kind of remove it coarsely, and then put it back in, and then use Otsu's thresholding algorithm to figure out what the mask is. That mask isn't great. It's going to be a lot better. There's a couple of different ways to do that, but preliminarily, it's able to improve the results of the deshadowing operation, and so there's something called the structural similarity index measure. The ground truth to the original image was about 0.46 across 4 different samples. And SSIM, -1 means completely unsimilar, 1 means perfect similarity. It was able to go from 0.46 to 0.71. Doesn't sound great, but that was at least a good step forward. And so there's a couple of ways that I'm going to be refining this. So firstly, modifying the loss functions a little bit more to prioritize robust features. Layer 22 in BGG16 has shadow robust features, and so it's able to take the most structurally important information and use that as a penalty. So in my previous slide, there was a little bit of corruption of some of the structural details. It's a little bit more visible on the laptop than it is up there. But BGG16 can help prioritize that so you're not actually losing structural information. 2 is transfer learning to refine results using an RGB dataset. And so a cool analogy for this is like tuning a wood instrument. Basically, you can use an RGB dataset to be able to get to some form of solution. And so that would be like the tuning pegs right here. It gives you like the relative pitch of what your solution is supposed to be like. And then after that, I can use a hyperspectral data set to fine tune it to what the solution actually is. And so that's what I'm currently working on right now. The benefit is RGB data sets are very widely popular, especially for shadow removal. And so I have access to a lot more information than what I can currently produce myself. And that gives me a mechanism for making my model a lot better. So once I train it using the RGB data set and I want to retrain on the hyperspectral data set, I freeze all the convolutional layers, and I gradually start unfreezing from the bottom up to be able to fine tune to the new task. The early convolutional layers don't need to relearn low-level tasks, which is why we use them to bring them to the correct pitch. But the later ones are responsible for very fine details, which is why we want to make sure that they're trained using the new data, and those are unfrozen. But yeah, it gives you a reduction in training time, so I'm able to train 3 times faster, and then dependence on a custom data set. And then lastly, using DynoV2 as a backbone for shadow detection to make my segmentation a little bit better. DynoV2 is a new model that Facebook AI came out with relatively recently that's able to do a lot of different things, such as feature mapping or segmentation. So you can use it as a backbone to segment images into different classes. And so my hope is if I'm able to fine tune it, using my data set, I'm able to get better segmentation results. That will help what I'm currently trying to do, which is a physics-based refinement. This is the second stage of my work. So again, the result of the GAN is somewhat coarse. It needs to be resolved even further in order to preserve like that spatial spectral information. And so that generated shadow mask is kind of a guide in order to refine the result even further. So there are 4 solutions that I'm currently focusing on. 1 is spectral similarity matchmaking. 2 is feature matching using k-means clustering or just any clustering algorithm. 3, nonlinear unmixing. So there's algorithmic, bilinear, p-linear, or k-height. Or deep learning, NNet or CMNAE. And then the 4th one is a context-aware module. Again, this will be building off of a backbone of like a pre-trained model. But the idea is, now that I kind of know where that shadow is using the GAN, I'm able to go through and iterate over patches and say, which patch is the most similar out of the ones that are not in the shadow region. And once I create that match, I can either replace it entirely or use its features to deconvolve. And get back up, basically impose its features on the shadow pixels. So this is like the naive approach, which I've started implementing, which is spectral similarity. This is patch-based matchmaking in 51D, which takes way too long. Basically, I'm iterating over each and every patch and then trying to find its closest neighbor, and it takes absolutely forever. And so the next approach, and I should explain, so the bottom is like the perfect shadow mask. And then there's the different spectral similarity algorithms that I tried. So there's spectral angle divergence, spectral information divergence, spectral correlation mapper, and then I think spectral information divergence, something of the sort. But basically, they allow me to classify an image into a couple of different regions, and I can kind of use that to impose some of the features that are within the same classification. The other thing is, if I'm able to reduce the dimensionality, go from 51D down to like 2 or 3. That would be really helpful for making this run a lot faster. And so principal component analysis helps do that. It basically transforms your data set to a new coordinate system, uses eigen decomposition, and so it gives you features that are uncorrelated and with the most variance. And so principal components, like the most important components of each pixel are given. And so once I have those, and it's in like 2D or 3D, I can cluster a lot faster. And so there's like a couple of different potential ways I can do that. There's k-means, which is pretty straightforward. Basically pick a mean within a cluster and then find what the closest neighbors are to it. And then there's also FISS, which is Facebook AI similarity search. This allows me to utilize my GPU in order to do all that clustering, which would make it a lot faster. But the goal is I find the closest non-shadow pixel within that cluster, meaning that it has the same features, and then either replace it or deconvolve it. Nonlinear unmixing is a technique that's specific to hyperspectral imaging, and so I'm able to decompose each pixel into its pure substances. And so in my case, I have like, on the left is an image that I have like tree, white background, foreground. And so that is what an N member is, right? So what is the percentage of this pixel in terms of the different N members? It's 40% tree, it's 20% white background. But I can decompose each pixel into fractions of that and then find the closest abundance ratio match in the non-shadow region. So if I find another pixel that's 40% tree, 20% white background, I can basically do that matchmaking. Lastly, a context module. This is something that I'm still kind of looking into, so it's partly a theory, but I can use an autoencoder network to downsample each 3x3 patch into a latent space, and then create a feature map. And then alternatively, I could also build off the backbone of DynaD2 for feature mapping. So below is an example of me just like quickly running an RGB version of my image through DynaD2, and it's able to like kind of cluster some of those pixels together. But once I'm able to create a feature map in the latent space, I can match using that. And so in that latent space, once I've created that match, I can again deconvolve and impose those non-shadow features on the shadow patches. That's all I have. Thank you very much.
Any questions?
Yeah. Do you have any questions?
Curious of how much is the camera?
I'm not 100%. I think it was around $20,000. And it's about this big. So it's a very tiny camera. It's from this manufacturer in Europe called Hubert. and not a lot of people use it. And so that's why it was like a very expensive item, because hypercycle cameras are only very large. So this is like the first portable version of it. It's still very slow, and so I hope that in the future, cameras will be that size and a lot quicker and a lot faster.
I'm not sure I'll understand your answer, but I'll ask the question anyway. I did an open CV project a few years back, and the training was kind of everything. I had to show these pictures are a bear, these pictures are not a bear. And do you think we'll get to the point where the training is going to be compressed, where I'll be able to instead of 1,000 of each, I'll be able to just have a few, and it'll make its own inferences about what's going to happen?
So there's a couple of different ways that I think that could be done. So one, you have pre-trained networks that already are really good at classification tasks, and then you do fine-tune, kind of like how I talked about before. So you only give it a few different images of bears, and it's able to kind of pick it up because it already knows how to classify a bunch of different things. It could be wildlife, it could be houses. So there's that. There's also like data set augmentation, and so you're able to feed it an image of the bear or change different things, like maybe make different colors or whatever. But you have multiple copies of your data. So that way you only realistically need like 10 or 15 images of bears. But your network will see different rotated versions or resized or flipped. And so that would help increase its prediction accuracy. So those are two different ways I can leave it. I'm sure there's a bunch of others, but that's like right off the table.
Have you looked into diffusion model?
Diffusion model?
Yeah.
Not particularly. What exactly?
So diffusion model was kind of getting popular this year. I mean, exactly 2023, and it kind of passed all the tasks, all the performance of all the tasks that was previously conducted by GAN.
Really?
Yeah. So I think I did a search and found out there are lots of work of deshadowing that's already done by diffusion model, and the general idea is that instead GAN used to GAN still reconstruct the whole image, but diffusion model, the idea is that from a raw image, you add, it's like the diffusion process, you diffuse the noise to the, so you add some Gaussian noise to an image. This is the first step. And the next step, you add more noise, and then until the image completely becomes a Gaussian noise. And then you train a model to reconstruct the added noise step by step, and then to reconstruct the original one. And it also has the ability to do conditional generation. So, like if you want to transfer from one domain to another domain, it can still work. And I think this is kind of like the shadow. Like the shadow is also a noise. So I think maybe there's something that can help.
Yeah, I've never really heard of diffusion models. That's really interesting.
Yeah,
I feel like if there is something that's already out there that's like pre-trained and I would be able to adapt it using my data, that'd be pretty interesting.
Yeah.
I'll have to look into that. Thank you so much.
So your title